So we can measure delta H experimentally. Calorimetry is a good way to do that. Or inferentially. We can infer it using Hess's law. We've just covered those two things. We can also calculate delta H using tabulated standard enthalpies of formation. Delta H is a change in enthalpy. We can define 0 to be whatever is convenient for us. Why is sea level 0 altitude? It's convenient, right? Now, granted, the ocean does go up and down. There's tides, but it's only a couple of feet usually, right? But the ocean is the same level all over the globe. I mean, what other reference could we use? We could measure from the center of the Earth. Exactly how would we do that, right? So that was chosen because it was convenient. We're going to choose 0 to be convenient in terms of energy. So we're going to measure changes in enthalpy compared to pure elements in their standard states. So basically we're saying, well, if we started with the building blocks as they are regularly found, and we make this thing, the change in energy can be measured relative to those initial starting blocks. So what is the standard state? The standard state is defined as a set of conditions. And we have to have different conditions for the different states, solid, liquid, and gas phases. So for a gas, the standard state of a gas is the pure gas at 1 atmosphere of pressure. For a liquid or a solid, it's the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest, which is usually 25 degrees Celsius. That's room temperature, basically. If we've got something in solution, it's that substance dissolved into a solution so that the concentration is exactly 1 molar. So there's a lot of ones here. 1 atmosphere of pressure, 1 molar, or pure substances. The standard enthalpy change, this is delta H0, so this degree sign up here means standard. The standard enthalpy change is the enthalpy change when all the reactants and products are in their standard states. The standard enthalpy of formation is the enthalpy change that happens when you make 1 mole of a pure compound at its standard state from constituent elements at their standard states. So that's also called the standard heat of formation, or enthalpy of formation. The elements have to be in their standard states. Elements in their pure standard states have heats of formation of 0 because that's the decided 0 point reference. So those are all 0. We measure enthalpy changes relative to elements in their standard states, just like we measure altitude relative to sea level. So this is a table from chapter 7 showing some standard enthalpies of formation for some different compounds and elements. And there's a much larger table in the appendix at the back of your textbook. So these are listed by different elements. Well, let's just start up here at the top. Here's bromine. Br gas, Br2 liquid, and HBr gas. So if we're looking at the element bromine, what do we know from looking at the periodic table? Is it a diatomic element? It is. So it's naturally found as Br2. And what does the color of its element symbol tell us about its state at room temperature? It's blue up there, right? It's a liquid. So the standard state for bromine is Br2 liquid. Here's Br2 liquid. It has delta H, heat of formation of 0. This is the standard state. Now this is also an element, bromine, but these are bromine atoms in the gas state. To get those, you have to do something. You have to break apart the bromine molecules, and so this is not 0. Where's the other one? There's carbon. So here's carbon. There's carbon graphite and carbon diamond. Two different forms of solid carbon. The graphite is considered the standard state, and so it has a heat of formation of 0. Diamond is not the standard state. It's going to be different in energy. So a lot of these we can guess what their standard states are, like sodium. We can look at the table here and find that the standard state for sodium is a solid. But we could get that off the periodic table, right? We find sodium over there. Is sodium a diatomic element? No. And what's its state at room temperature? It's a solid. So solid sodium is going to be 0. If we look at something like I don't know, nitrogen. Nitrogen has got a red symbol on the periodic table. Means it's a gas at room temperature. Is nitrogen a diatomic element? Yes, it is. So we should not be surprised here with nitrogen that the standard state is N2 gas. Okay. So the standard heats of formation represent the enthalpy change for forming that thing from its elements. So if we look at the at methane, we can look up in the table that the heat of formation for methane is negative 74.6 kilojoules. We can write a chemical reaction for the formation of this using the elements in their standard state. So this has 1 mole of carbon in it. So I'm going to use 1 mole of carbon in its standard state, the graphite. And I need 4 hydrogen atoms. I need hydrogen in its standard state, which is H2 gas. So I'm going to use 2 of those. When we write a formation reaction, the coefficient on the product always has to be 1, because we're talking about the energy to make 1 mole of this thing. That results in us sometimes having fractions over here, and it's okay. So like this says, if you're not sure what the standard state of the element is, find the form in Appendix 2B in your textbook that has delta H equals 0. That's the standard state. We always write this for 1 mole of product. So let's look at carbon monoxide. Writing the formation reaction. So we're trying to write this for carbon monoxide, CO, in the gas state. There are 2 elements present, carbon and oxygen. So we've got these as reactants, carbon and oxygen. But we need to identify what their standard states are. So there's more than one state for elemental carbon, but the one with delta H is 0 is graphite. So C, graphite. Oxygen's standard state is a diatomic gas, so we put that in there. Is this a balanced chemical equation? No, it isn't. We need to balance it, but we have to keep the coefficient of our product 1. So if I want to make 1 mole of carbon monoxide, I'm going to use 1 mole of carbon and half a mole of oxygen. It's like half a dozen eggs. You can do that. Right? And we look this up in the table, minus 110.5 kilojoules per mole.
You look up this carbon plus oxygen?
I'm looking up CO. These are both 0. So if we go back and look at the table, under carbon, here's carbon monoxide. The heat of formation for that is minus 110.5 kilojoules. That's to make 1 mole of carbon monoxide.
And how did we know to multiply by 1/2 instead of with another constant?
Well, we need it to be balanced, and we need the coefficient on the product to be 1. So we always want to make 1 mole of our product. So let's look at this unbalanced one here. I've got my elements in their standard states, and this is the compound I'm making. It's not balanced. Normally what we would do is we'd put a 2 over here and a 2 over there, and we balance it that way. This is a little different because we want to end up with 1 of these. So I've got oxygens coming in pairs, and I only want 1 of them. I need half of it. Okay? If it makes more sense to you, you could go ahead and balance it the regular way. I'm just going to say solid. That's how we would normally balance that equation. And then I recognize that I need this to be a 1. So I'm going to divide this by 2, and divide this by 2, and divide this by 2. And I'll end up at the same place. But that might make more sense to some of you. So, yes?
So we're just balancing that, not writing what the change in
Well, I'm writing the equation here, the formation equation that goes along with that enthalpy change. Let's see if I can get back there. So the value that I look up in the table is for the formation of 1 mole of the compound. This is the chemical reaction that corresponds to that, the chemical equation. So you might be wondering, why are we doing this? We can look these up in a table, and we can find what we need and put them together using Hess's law to find the delta H for pretty much any chemical reaction without doing any experiments at all. That's where we're going with this. Write equations for the formation of sodium chloride and lead nitrate from the elements in their standard states. Include the values of delta H. Well, let's just write the equations first. So, for sodium chloride is our product. And what are the elements that are present in it? Sodium and chlorine. So here's sodium and chlorine. What's the standard state for sodium as an element? A solid, and it's not diatomic. What about chlorine? Is it diatomic? Mm-hmm. And what's its state at room temperature? It's a gas. So those are my 2 elements in their standard states. If I have troubles figuring out what the standard states are, I'm going to go look at the table and find the one that has 0. Now I have to balance this. I want to keep 1 mole of sodium chloride. So how can I get one mole of chlorine when they're coming in groups of 2? Half. Right? So this is going to be 1/2. We'll go look up the numbers in a minute. So lead nitrate. I'm going to write the formula over here. What elements are present in that? Lead, nitrogen, and oxygen. Okay? So lead, nitrogen, and oxygen. What's the standard state for lead? Well, it's a metal. It's not diatomic, just Pb solid. What about nitrogen? It's a gas and it's diatomic. And oxygen, also diatomic, also a gas. And now I balance. I need 1 lead, and I've got 1 lead here. How many nitrogens do I need in 1 mole of this? How many moles of nitrogen? 2. 2 moles of nitrogen. Oh, well, that'll work out just fine, right? And then how many moles of oxygen? 6. I need 6 moles of oxygen atoms, and here I've got 2 moles. So if I multiply this by 3, I'm just going to move that over a little bit. So I'm going to balance these by not writing anything on the right side. I'm only going to write coefficients on the left side. Any questions about that? Now it says include values of delta H. So now I have to go back and look these up. Oh, actually, did I not do that? They're not in that first table, so lead nitrate, this is from appendix 2B, lead nitrate, PbNO2, solid. Now this table gives heat of formation. It gives delta G, 0S, and F, and S0. These two we're going to use in Chem 1B, so just ignore those. So lead nitrate minus 451.9. Now it's not going to let me go back and fix that one. I think I can figure out how to do it. There, I got it back. So the standard heat of formation for this one was minus 451.9 kilojoules. And whoops. For sodium chloride, sodium chloride I think is on that other one. I need to find a better way to do this. Sodium chloride's in this one, minus 411.2. Yeah.
Does that refer to the energy that needs to be put into the equation to have that product, or the amount of energy that's produced at that reaction?
That's a good question. So is it the amount of energy put in or the amount of energy released? The sign tells us that. So this one has a negative sign, which means that when you form sodium chloride from its elements, it releases energy. And when you form lead nitrate, it releases energy. Most compounds will have a negative heat of formation, meaning energy is released. But there are some that have positive. Yeah, good question. Any other questions? So the heat of formation, standard heat of formation, corresponds to the formation of a compound from its constituent elements, right? So we take the elements, we make the compound, we look up the heat of formation. Well, if I write that backwards and put the compound, and I'm taking it apart into its elements, the energy change then is the same number but opposite in sign, right? If it released 411 kilojoules when it was made, I'm going to have to put 411 kilojoules in to break it apart back into its elements, okay? So this allows us to calculate enthalpy changes without even combining all those chemical equations, because that can get a little tedious and confusing, right? Some of you might find that it's fun. I think it's kind of fun. It's a puzzle, but it can be time consuming, especially if you aren't handed the exact 3 things that you need and you're trying to look them up in a table. And the table in the back of the book is pretty big, but the table in the CRC is pages and pages of those things. Think of all the hours of work that people put in measuring that stuff. So any reaction can be written as the sum of formation reaction or the reverse of formation reactions. And so we can find the heat of reaction, standard heat of reaction is the sum of those heats of formation values for the component reactions. So this is the fancy math way of expressing it. It's the sum of the coefficient times the heat of formation for the products minus the sum of the coefficient times the heat of formation for the reactants. It's minus here because any compound that's a reactant, we're going to be taking apart, right? So we have to change the sign. So let's look at an example. So here we have the combustion of methane. Methane combining with oxygen to form carbon dioxide and water.